So good evening, Carolians and guests. This is a talk about the LSST. So does LSST stand for the Large Synoptic Survey Telescope, or does it stand for the Legacy Survey of Space and Time? We can swap it back and forth as we wish, and arguably it stands for both. So I'll be using the acronym LSST as if it stands for the telescope, and I'll be saying something about the confusion over the acronym right at the end. Okay, so what am I talking about? Sky surveys generally. Why do we want to survey the sky? And I'll say something about existing surveys. Then we'll move on to the LSST, the Large Synoptic Survey Telescope. Why do we need another survey, and why do we need an explicitly new telescope to do this survey? I'll be touching on some of the science that the LSST will deliver, and then looking at the technology that will deliver that science, the optics and the camera. And then I'll say something about the operation of how it's going to do the survey and what's going to happen to the data. So we can ask the question, what's out there? Pretty fundamental question. That's what most astronomers are interested in. What's out there? And to answer that question, you might say, well, don't all telescopes pretty much answer the question as to what's out there? And the answer is, well, no, not really. Because most research telescopes look at known objects. In other words, objects that have already been observed and catalogued. Only a few survey telescopes actually look to find out what's out there rather than look at something we already know about. So surveys of everything in the sky, and by everything I mean everything that can be seen from a given location down to a certain limiting magnitude, surveys have been carried out a few times over the last 100 years or so. If we go back to the middle of last century, the Palomar Observatory Sky Survey in the 40s and 50s used photographic plates on the Schmidt 48-inch at Palomar Mountain. Some 2,000 photographic plates were taken, covering the whole sky in about 10 years. That was repeated some decades later by the second Palomar Sky Survey, and here they used improved emulsions, red sensitive and blue sensitive plates that were a little more sensitive than the ones in the 40s and 50s to give better coverage of the sky and to go a little deeper, fainter objects. In this millennium, things went digital with the Sloan Digital Sky Survey, taking again more than a decade or so, this time with 2-meter class telescopes and the photographic plates replaced with CCD cameras, and some 1 million images were taken. Overlapping in time with that was the Pan-STARRS survey. You can see it occurred in a few years that overlapped with the last years of the Sloan survey. And Pan-STARRS is an acronym standing for Panoramic Survey Telescope and Rapid Response System. The idea being it would survey the sky and catch, for instance, asteroids and comets. And here we're talking about the LSST, if you like, the fifth in this series of sky surveys, the Large Synoptic Survey Telescope. The word synoptic is almost synonymous with survey. It means we're getting the big picture of what's out there. And the nominal period of this survey will be of order now for the next 10 years. Okay, things might have slipped a little bit over the last year or two for obvious reasons, but it's nominally a 10-year project. So why do we need another one if we've already had 4 in the last 100 years? Well, if we look at how many objects have been surveyed as a function of time, what's the sort of gold standard, what's the holy grail for how many objects we would like to include in the survey? Well, we can draw a notional ceiling there because there are of order 100 billion stars in the Milky Way, and roughly speaking there are of order 100 billion galaxies in the observable universe. So that's a useful sort of yardstick, or if you like, a sort of holy grail as to where we would like to get. So where have these surveys got us so far? Well, the Palomar survey did something like 100 million objects, mainly stars, a few galaxies as well. The Sloan Digital Survey improved on that and got us up to somewhere between 300 million and 1 billion objects. Pan-STARRS improved on that again and took us to about 3 billion objects in the survey. So how is the LSST going to build on that? Where would we hope the LSST will be on this graph? Well, we're hoping it's going to be somewhere there. Not quite at the grey line, but pretty damn close. It's going to end up cataloguing more than 30 billion objects. That's a fairly large fraction of all the objects that we think are there in terms of stars that we think are in the Milky Way and galaxies in the observable universe. So if this is supposed to be starting fairly soon, obviously the preparation has been going on for quite some time now, the last decade or two, and we are currently roughly where that red arrow is, just about to start operation. In other words, most of the construction is complete. Operation was due to start in 2022. That might well be delayed, but hopefully not by too much. So, why can't we simply use whatever telescopes happen to be around? There are, of course, hundreds of telescopes dotted around the world. Why don't we just use one of those for the survey? Well, if we want to survey the sky with a particular combination of telescope and camera, we need three basic characteristics. We need the system to have a nice wide field of view. If there's a very narrow field of view, it'll take us ages to map out the whole sky. It must be fast in the sense of the optics must be fast to keep the exposures short, again, so that we can survey in a reasonable length of time. And it must be deep in the sense of we must be able to see faint objects. So we need wide fields of view, we need fast optics, and we need to be able to look at faint objects. We need to be able to see faint objects. To some extent, we can trade off a little bit of one of those characteristics against the other, but if we want the best possible survey telescope, then it has to excel in each of those three areas. Wide angle is fairly obvious, faint objects hopefully fairly obvious, but what do we mean by fast optics? That's perhaps familiar to photographers. Fast in this context means if we quantify the focal length of the optical system divided by the diameter, this so-called F number. If the F number is small, that means we have a large diameter for a given focal length, and that produces bright images. And if the image is bright in the photographic sense, that means we can have a short exposure or a fast shutter speed. So because of the way photographers think, the idea of optics having a large diameter for a given focal length, because that leads to fast shutter speeds, that then gave this set of optics the nickname fast optics. Let's just have a look at a few numbers. Let's just take a hypothetical situation. If we wanted to photograph something and it required an exposure of 1 minute, if we had an F number of 2, in other words, the focal length twice the diameter of the objective, doesn't matter if it's a lens or a mirror. Then if we went to larger F numbers, in other words, smaller effective objective size, objective diameter, then we would need longer exposures. So for those of us who dabble in astrophotography, we tend to choose a lens. If it's a wide-angle lens, for instance, we'll choose one that has a reasonably fast F number, maybe F2, F2.8, F4 perhaps, in order to collect as much light as possible and give us bright images and short, relatively short exposures. How do those F numbers compare, for instance, to telescopes? If we think of the Hubble Space Telescope, it has a mirror diameter of 2.4 meters and a nominal focal length of order 57 meters. So if we take the focal length and divide it by the aperture, the diameter of the mirror, 57 divided by 2.4, that means that the F number of the Hubble Space Telescope is somewhere around F22. In other words, it is by no means fast in the optical sense. So you might say, okay, that's the Hubble, but surely with a larger mirror we can get faster F numbers. What about the European Extremely Large Telescope? It's got a whopping 40-meter diameter mirror. Surely that's going to be a lot faster. Well, it is a much larger mirror for sure, but its focal length can be anything up to 750 meters. Divide one by the other, we find that the European Extremely Large Telescope might be operating at something like F16. So, large ground-based or space-based telescopes are not necessarily optically fast. and also they have rather limited fields of view, so they're not ideal for survey telescopes. If we think about wide, fast and deep, the characteristics that we want, if we've got in our back garden a camera with a wide-angle lens, that will certainly get a large chunk of sky, but generally speaking they won't be particularly fast optics and they won't look at very faint objects. A camera with a telephoto lens might be able to get you very distant objects. For instance, with a telephoto lens, I photographed a quasar which is some 25 billion light years away. So you can indeed image very distant objects with a telephoto lens, but you're restricted to not a particularly wide field of view and, generally speaking, not particularly fast. We've just seen that the Hubble Space Telescope and the Extremely Large Telescope, as just two examples, are very deep in the sense that they can look at very faint objects, but they're not particularly fast. The exposures can't be really short because the optics aren't fast. And the field of view of both of these telescopes is going to be very restricted, so they're not wide angle. The LSST should tick all three boxes, which is why the mantra of the LSST project is wide, fast, deep. Large chunks of sky, very quickly, getting very faint objects caught in each image. And that's what it will look like. Still an artist's impression. It is actually now built, but not quite complete. The telescope has a very large mirror, considering its focal length, which is why the telescope looks rather stubby. And a very large camera sitting behind the secondary mirror, which I'll come to in due course. So one of the key aspects of the project is that the whole sky will be imaged every 3 nights. Remember, the Palomar survey effectively imaged the entire sky that could be seen from Palomar, but it took a decade. The LSST will cover all of the sky that can be seen from the observatory in 3 nights. In other words, it'll cover approximately 1/3 of the sky every night. Hence, every patch of the sky, because it's a 10-year project, every patch of sky is going to be imaged many times during the 10-year survey. It's not going to be, we've seen that, we've got a picture of it, end of story. It's going to be re-imaged over and over and over again, hundreds of times, if not thousands of times, during the lifetime of the project. So it's not simply that the LSST will catalogue a large number of objects, tens of billions of stars and galaxies. It's not simply the sheer size of the catalogue it'll generate. It's the fact that it will catalogue not simply the brightness of that star or the colour of that star. It will be able to catalogue changes because it will be looking over and over and over again. It's the timescale over which the LSST will operate that makes this so different from all previous surveys. It will provide us with a wealth of data on a number of different areas. For instance, it will be looking at objects within the solar system, it will be looking at stars within the Milky Way galaxy, and it will be looking at galaxies throughout the observable universe. To do this, it will need a novel telescope, indicated by the picture on the right-hand side there. It looks a little different to many other telescopes you may have seen. It will require the largest camera yet constructed. And at the end of this talk, I'll say something about the difficulties of handling the huge amounts of data that it will produce. It will generate the largest catalogue of astronomical objects ever, and these will underpin, in years to come, if not decades to come, the objects that are surveyed by this telescope will underpin research projects carried out by large ground-based telescopes, such as the EELT, and future space telescopes, or existing space telescopes like the Hubble and the Webb, and whatever comes next. So what are the principal scientific aims of the project? If we think on a relatively local scale, it will effectively take an inventory of the solar system. That in turn will clarify the history of how the solar system formed, and it may well help us understand exoplanet systems as well. Within the Milky Way, it will be looking at stars within the Milky Way, which will help us determine the structure and the evolution of the Milky Way. and it will find the properties of many stars within the Sun's neighbourhood. You might say, well, isn't Gaia doing that? Gaia is mapping out the positions of various stars in the Milky Way. Well, yes, indeed, Gaia is doing that to a fantastic precision, but the LSST will be able to look at fainter stars. Gaia has a magnitude limit, LSST will go beyond that and to look at much, much, much fainter stars, down to magnitudes of 25, 26, 27th magnitude. On a larger scale, on a galactic scale, the LSST will catalogue, it's expected, something of order 20 billion galaxies. It will be looking at individual galaxies as well as galaxy mergers and galaxy collisions, which will help us understand galaxy evolution. And for the more nearby galaxies, it'll help us understand star formation processes. By looking at gravitational lensing, the LSST will be able to study the existence and the distribution of dark matter. And the existence is almost irrefutable now, but we really don't know much about where all the dark matter is, and the LSST will hopefully help us answer that question. By looking at different distances, you're looking back in time, so if we can see where the dark matter is as a function of time, we can get a handle on what dark energy is doing in our universe, because that will affect the way that dark matter behaves. Now, at the moment, it looks like dark energy is starting to rip the universe apart. It's accelerating the expansion of the universe. It would really be nice to understand what that is. We can do that in part by studying dark matter, and in part by looking at supernova. In distant galaxies, that gives us an idea of the acceleration of the expansion of the universe. So far, all of the telescopes on Earth in total have found something of order 1,000 supernova. When the LSST is operational, it should detect 1,000 supernova every night. So on its first night of operation, it's expected that the total number of supernova we know about will double, and it will continue detecting thousands of supernova every night for its entire 10-year lifetime. Within the solar system, it's sobering to realise that a single exposure could detect up to 5,000 moving objects. So in other words, in addition to all the stars that it sees, in addition to all the galaxies that are seen, in a single exposure there might be some 5,000 moving objects. It might be that number has to go up a little bit when you take into account all of the various constellations of satellites that have been launched recently. And this could indeed be a major problem, trying to separate the interesting objects from all the boring satellites that we know about. In the 10-year survey, it's expected that the LSST will map out some millions of asteroids and trans-Neptunian objects. Some 100,000 near-Earth objects will probably be found. Some of them we'll already know about. The brightest ones we will already know about from other telescopes. It's the fainter ones that we have to really keep an eye on. So we know that there are quite a few asteroids that cross the Earth's orbit and are potentially hazardous. In addition, there's various objects in the outer solar system. If we think of the terrestrial planets and then zoom out to the gas giants and the ice giants and then zoom out again, we see that there are various objects in our solar system at great distance, these trans-Neptunian objects, some of them in very peculiar orbits, which would indicate the existence of Planet 9, because if there is a ninth planet out there, that will be affecting these objects and giving them these rather peculiar orbits, peculiar in terms of eccentricity and their inclination to the ecliptic. So if indeed there is a Planet 9 out there, it is thought that LSST will find it quite quickly. It's almost impossible for LSST to miss it, assuming we've got the predictions of approximately its mass and its position roughly right. What about the Milky Way? Well, looking at a galaxy from the inside is not as easy as you think. In some sense, it's easier to see what's happening in Andromeda than it is in terms of finding out what's going on in the Milky Way, simply because we're on the inside and we don't get that great a view. Indeed, it's only relatively recently that we figured out that the Milky Way has got 4 spiral arms. Before that, it wasn't clear whether it had 2 or 4. There's Herschel's picture of what he thought the Milky Way looked like based on looking at the Milky Way from the inside. So that's what we think the Milky Way looks like. In the centre there is the centre of the galaxy, and we are down there sitting in between 2 spiral arms on what is called the Orion Spur. It is thought that a single exposure of the sky, in other words, an exposure taken of the entire sky, it might have to be done over a few months, because of course you can't see the entire sky at any given time, because you have to let the sun get out of the way, so you need to observe in different months. But once the entire sky has been surveyed once, we think that the total volume that had been surveyed will be some 10 times larger than any previous survey. And by the time you've been over the sky more than once and you start to co-add all of the various images to get fainter and fainter and hence more distant objects, it is thought that the survey volume will be some 1,000 times larger than any previous survey. As a spin-off, it's not really the main aim of the LSST, but one of the spin-offs will be, because you're looking at many billions of stars, almost certainly you're going to catch a few exoplanets, as it were, by accident. It's not what it was designed for, but simply as a spin-off, when you monitor the brightness of lots of stars and go back and look at them every few nights, you will find that you do pick up a few extra exoplanets. It's thought that there'll be probably a few discoveries of exoplanets in the Magellanic Clouds, which will be the first confirmation of an exoplanet in another galaxy. You may have heard recently about a discovery of a possible exoplanet observed in X-rays, but that can't be confirmed for perhaps a few more decades. So any exoplanets that are found, again, they will be passed on, and if they look interesting, perhaps the James Webb will end up looking at them in more detail. We know that interactions between galaxies are more common than we first thought. The Hubble Space Telescope over the last 30 years has been imaging in wonderful detail lots of galaxies, showing us that galaxies interact with each other. And we think that's a major part of galaxy evolution. Galaxies don't tend to evolve in complete isolation, they tend to interact. There are gravitational forces, some galaxies will collide, some galaxies will merge, and we think that's how galaxies grow. If you look at this particular galaxy, M63, you look at that and you think, well, that galaxy is on its own, it's isolated, it's not interacting with any other galaxies. But if I just take the colour away and invert the black and white to the opposite, and then boost up the contrast a little bit, you see all of these wisps that seem to be in the background, as it were. These are telltale signs that this galaxy has interacted with other galaxies in the past, and the tidal interactions of possibly merging with another galaxy and possibly simply another galaxy passing by has produced these tidal wisps or tails that are coming out of this galaxy. So even a galaxy that looks at first sight to be isolated actually contains clues as to its history. And we can see that in this case as well. If I do the same, invert it and boost the contrast, you can see the main part of the galaxy has these huge tails, which are in some cases larger than the galaxy itself, indicating some of its past history. The LSST is certain to find lots of galaxies with these faint tidal tails, and not just in a few galaxies, but if you survey billions of galaxies, you're likely to find a large number of examples where these structures are visible, and that will help us understand galaxy evolution. But what about the dark universe? As far as we can tell, only 5% of the universe is made up of stuff that we can see. Ordinary matter that we're familiar with, stars, dust, gas, etc. 20% of the universe, as best we can tell, is dark matter. We know dark matter is there because we see its influence on, for instance, the way galaxies cluster or the way stars rotate around galaxies. But we don't know exactly what it is. Well, actually, we haven't got a clue what it is yet. And we don't know exactly where it is. 2/3 of the universe is the more mysterious dark energy. We think that dark energy is causing the expansion of the universe to accelerate, and ultimately it looks like it'll rip the universe apart. But we don't know what that is either. So if this so-called dark sector accounts for 95% of what's out there, then we really ought to get a handle on this and understand it rather better. So we believe that dark matter forms a sort of cosmic web, a dark web if you wish. We believe that because that seems to be what simulations are telling us. If we run a computer simulation from the very early universe to the present day, it indicates that the dark matter ought to form a sort of filamentary structure, a web-like structure, and where these filaments cross each other, that's where galaxies and galaxy clusters and galaxy superclusters will start to form. So we think that's what the dark web looks like, based on simulations, but it would be nice to actually verify that that is indeed what the universe looks like. So is the dark matter uniformly spread throughout a galaxy? Is it spread in the halo around a galaxy? Is it blotchy? Is it clumpy, as this artist's impression would indicate? Well, hopefully we'll start to learn more about that when we can see where the dark matter is. How do we map out the dark matter? Well, that can be done with gravitational lensing. In these little simulations, the orange galaxies are in the foreground and the blue galaxies are in the distance, and the orange galaxies in the foreground, the mass of those galaxies is distorting the image of the more distant galaxies by gravitationally bending the light coming towards us. If I just run that simulation again, and the amount of dark matter that's present will determine how much distortion of those distant galaxies we get. Less in the top case, more in the bottom case. So if the LSST looks at lots of distant galaxies and we look at the distortion of the more distant galaxies beyond them, then we'll get an idea of where the dark matter exists. And if we do that as a function of distance, which is in effect a function of time, we'll get a handle on dark energy as well. We don't have to look for very strong distortions, as I've indicated in those two videos. The LSST, some of the power of the LSST will come from the fact that we can use so-called weak gravitational lensing. And that's the idea that even if you haven't got a huge mass like a galaxy cluster distorting the image of more distant objects, even just one galaxy on its own will produce a very weak distortion of what's in the distance. So here we have a web of dark matter indicated in red, and we have a few other galaxies. But remember, we can't see the dark matter, so we can't see the web. What we can see are individual galaxies. And what the LSST is going to do is to map out the positions and orientations of various galaxies, which will be influenced by the existence of the dark web that we can't actually see. In other words, the dark web is there and it will distort those galaxies to some extent or another, maybe only by a tiny amount. But if we look at enough galaxies, not a few dozen, not a few hundred, not a few million, but if we look at billions of galaxies, even if the distortions are very small, we will be able to see them and work out what the structure of the dark web is based on the galaxies that we can see. And that will also give us information about dark energy, because dark energy influences the way dark matter ends up as structures within our universe. So that's something about the science, but how can that science be delivered? We're going to need a telescope with a unique optical design. We're going to need the world's largest camera, and we're going to need an outstanding observatory site. So where's this going to be placed? Well, the best observatories in the world are based on one of three locations, either the volcanic islands of Hawaii in the Pacific Ocean, or the Canary Islands in the Atlantic Ocean, or the high desert of the Atacama in Chile. Those are the three best sites in the world. And for the LSST, it was chosen to place it in Chile. So that's where it's going to be, where the red flag is there in the Atacama Desert, Charapason. No, that's not the telescope itself. This is the view from the site of the LSST looking across to the neighbouring mountain. That observatory you can see on the neighbouring mountain over there, that is Gemini South. So Gemini North is the telescope in Hawaii, Gemini South is here in Chile. It's such a good observatory that they decided to use the neighbouring mountain for the site for the LSST. So the first thing they did is blow the top off the mountain and then get lots of people in to start sucking in through their teeth saying, don't like the look of this, but they decided that was a good, nice, solid bit of rock onto which to build the LSST. So that was some years ago. They started construction. That was, I think, 2019 when most of the observatory was complete and the turret was being put together. And the latest picture I could find, it is slightly behind schedule because of COVID, but you can see that construction is well advanced. A slightly different view, this time a simulation, because this one shows the little observatory on the right, which is a smaller telescope which is used to check sky conditions to make sure that the main telescope is surveying an appropriate part of the sky, which is as dark as it could be. In the main turret there you can see that's where the telescope is going to be, and the other equipment in the rest of the laboratory is the optical laboratory for instance, recoating the mirror, which will need to be done every once in a while. So let's think about this optical design. We want a wide field of view, but there's no point in having a wide field of view if it's distorted and aberrated at the edges. We need it to be pin sharp over the whole field of view, and it was decided that they want a field of view of more than 3 degrees to make sure that they can cover the entire sky in 3 nights. And that required a rather novel 3-mirror design. The primary mirror diameter is about 8 meters, the effective focal length is about 10 meters, and that gives you an F number of 1.2, so very fast, even by the standards of fast photographic lenses. That is very fast. Let's have a look at the optical design here. Let's just take that down a little bit. Light hits the primary mirror and then bounces up to a secondary mirror and then comes down to mirror number 3. And this is where it's rather odd. Mirror number 3 is the same piece of glass as mirror number 1. In other words, a blank piece of glass was ground to a certain shape to produce mirror 1, and then the centre of the mirror was ground to a different shape to produce mirror 3. That means, of course, mirror 3 can never get out of alignment with mirror 1, making collimation so much easier. After bouncing off mirror 3, it then goes into the camera. So this is the mirror being made. Lots of chunks of glass are put into a mould in a furnace, and then in this case the furnace is spun. This has the advantage that you end up with something close to a parabolic shape as the glass melts, and then it forms a parabola as it spins, and then as it cools off you get a curved shape, which means you have to then grind less glass away to get the final figure that you want in the mirror. Cameras looking into the glass as it was melting show these various glass blocks melting and then dropping into the rib structure that you can see inside the mould. There it goes, the glass melts and then sinks into the rib. And again, the glass melts and then sinks into the ribs. One more time in this video, the glass melts and then sinks into the mould. So that's video showing you what was happening as the glass was melting, and then it would slowly cool down, and that's what then comes out, an 8.4 meter blank. So this eventually will be figured, was figured to the shape of mirror 1, and in the centre, mirror 3. Okay, so some very interesting optics gives you a wide field of view, but of course that's wasted unless you can actually catch all of that in a large detector. So no, that's not it. That, just for scale, is a reminder of probably the smallest camera that you own. It's the one in your mobile phone. That's typically the size of a mobile phone camera, the lens and the chip just behind it. And if I make to scale from that, this is the size of the chip in the Hubble Space Telescope. So here it is for real, if you can see my image there, 4 centimeters by 4 centimeters, 40 by 40 millimeters. The Hubble chip in camera number 3 is a 16 megapixel chip. Probably a little bit larger than one in your digital camera. If you have an SLR or a mirrorless camera, you probably have a chip which isn't a huge amount smaller than that. So yes, that would be a nice size to have, but a few centimeters on a side is not that unusual for people's cameras. So that's the 16 megapixel detector in the Hubble. Let's just put that there. Let's imagine taking those 16 megapixels and adding another 8 of the same around it into a sort of package. Now let's imagine taking that package with 9 lots of 16 megapixels. Let's take that package and add another 8 of the same. And then add another 12 of the same. Now add a few chips that are used to check focusing and tracking, and now you have the detector of the LSST. It has in total 189 imaging sensors, 8 guide sensors, 4 wavefront sensors, in other words focus checks, and it ends up as an array that's 0.6 meters on a side. So the image that's obtained from this detector is 3 billion pixels, more than 3 billion pixels, 3 gigapixels, and the information is read out from the chip in 2 seconds. It's difficult to really appreciate the size, so let me just remind you that this is the size of the Hubble chip, and let me show you a mock-up of the same thing to scale. There's the size of the LSST detector. So here is the Hubble chip, which you can just about see, and here is the LSST detector. I can't even fit it in the camera. When we talk about the size of a coffee table, that is indeed what we mean. 3 billion pixels in a detector that's 0.6 meters on a side. Now, of course, I can't possibly show you the sort of images that we're expecting to get from this camera because I've only got a few megapixels in this particular monitor, and Zoom won't allow me to show you anything at higher resolution. So let me just show you what we would expect to get in a simulated picture just from the black square there that you can see on the left-hand side there. So a very small fraction of the total detector, what we would expect to get in a single 15-second exposure is something a bit like that. We would expect to get a large number of stars and a large number of galaxies in a 15-second exposure. And remember that the full image obtained in those 15 seconds is larger than what you're looking at in terms of area by a factor of some 3,000. So just mentally absorb what you're looking at, multiply by 3,000, that's what you get in a 15-second exposure. Truly phenomenal amount of data that's going to be coming out of this system. A reminder of the field of view on the sky, if we think about the size of the moon, 1/2 of a degree, then that's the size of the Hubble Space Telescope field of view. Remember, not particularly fast and very narrow field of view as far as mapping the sky is concerned. So narrow, in fact, that if you wanted the Hubble Space Telescope or something like the James Webb Space Telescope to map everything in the sky, it would probably take centuries to do that. So what is the field of view of the LSST, the 3 degrees? Well, too big for this particular view. The best I can do is to show you the edge of the 3-degree field of view, and that gives you an idea of the sheer area that's covered compared to the area of sky that's covered by the Hubble. It has filters, and there are nominally 6 filters called UGRIZI because of the labels given to each of these wavebands. You can see that it covers a little more than the visible spectrum. There's 1 filter in the UV, a couple in the visible, and 3 filters in the infrared. So information can be obtained about the colour of stars, not necessarily the colour of galaxies, but yes, that could be used in principle to give us an idea of redshift, in addition to using the filters to give us an idea of the colours of stars. Objects that are bright in the infrared, again, if they turn out to be interesting, then maybe the James Webb can go and have a look at those. That gives you an idea of what the camera looks like in terms of scale, as shown by the decapitated man on the right-hand side. It also reminds you that the filters that are used are absolutely enormous. They have to be large enough to cover the entire chip. I believe that it takes 2 people to lift one of the filters. The filter interchange system can change filters not particularly quickly. You don't want to change filters back and forth too often. You will probably take quite a few images with one filter, and then you will decide to change the filter and then take a few more images. You won't be changing filters back and forth because it wastes a few seconds of valuable imaging time. Roughly speaking, what is it going to look at? Well, it's going to be imaging as much of the sky as it can see. Being in Chile, of course, it's not going to see much of the northern hemisphere. It'll see a great deal of the southern hemisphere. The colour scheme here tells you, roughly speaking, how many times it might visit each patch of sky. So for most of the southern hemisphere, it's going to be visiting each patch of sky many hundreds of times, perhaps, looking at the colour there, perhaps 900 times throughout its 10-year survey. Note that the south celestial pole is green. It's not going to be imaged as many times. Why are they not interested in the south celestial pole? Well, mainly because it's low down in the sky. From the latitude of Chile, the south celestial pole is not that high in the sky. There's no point in imaging when you're looking through a lot of the Earth's atmosphere. They're making an exception for the galactic plane. They want to follow that as far as they can, and they want to make sure that they don't miss too much of the ecliptic. So of course the ecliptic is partly in the southern hemisphere, partly in the northern hemisphere. You can see this green area in the top left there. They're trying to make sure that they include all of the ecliptic because that's where most of the interesting solar system objects are going to be. Some of the objects are dark blue rather than light blue. You see indicated there this idea of a deep drilling field being a little bit darker blue. In other words, if any of the astronomers find anything particularly interesting, they can ask for more images to be taken, or images to be taken more often, of particular objects of interest. For instance, the Large and Small Magellanic Clouds are going to be looked at more often than surrounding areas. So there are schemes for what objects are going to be looked at and how often any given object is going to be revisited during the lifetime of the project. So let's have a think about what they do with all of this data. The LSST is going to generate shed loads of data, and shed load, by the way, is an accepted SI abbreviation for lots. How is it going to be stored? Well, remember how you store information. Does anybody remember these things? Yeah. Just as a point of reference, floppy disks can store about 1 million bytes of information. That's a good place to start. A megabyte or so, 1 million bytes of information, which of course is barely enough for one digital photo these days. So there's a picture I took on Safari of some nice zebra. It's a 2 megapixel image after I've reduced it from its original size, and it occupies about half a megabyte. So I could store a couple of those on a floppy disk. But alternatively, I could say, well, floppy disks are too passé. What if I go to a digital versatile disk? A DVD can store many gigabytes of information. So that's equivalent to thousands of floppy disks. So I could store most of a Safari's worth of images onto a DVD. I could quite happily store many thousands of images on a DVD. But if, ridiculous though it sounds, we decided to store the output of the LSST on something like DVDs, how many could it possibly fill up? How long would it take the LSST, if it stored its data on DVDs, something like 4 gigabytes per disk, how long would it take to fill up that much data? It would take about half an hour, and then it would have stored that much information. So we have to move on to something else. For instance, we could go with, well, inside your personal computer is probably something like this, a terabyte disk. A terabyte is 1,000 gigabytes, a gigabyte is 1,000 megabytes. So a terabyte disk is equivalent to many hundreds of DVDs. So that's a little more plausible. But even that is a tough ask, because if we think about what the LSST is going to be doing, one night of observations will produce enough data to fill 20 terabyte disks. And in Chile, it's probably going to be clear most nights of the year. So let's say we multiply that by 300 or more clear nights in a year, and it runs for 10 years. So how many disks are we going to need? Well, it's been estimated that the total data storage is going to need to be of order 500,000 terabytes. That's by the time you've added in calibration data, darks and flats, etc. Now, they're not necessarily going to be using terabyte disks. We would hope that in a few years' time something better will come along, but you can get an idea of the scale of the problem if you've got to allocate 500,000 terabytes to the project for the storage of its data. So an exposure is going to be 15 seconds. Over the chip that I've shown you, over the detector that I've shown you, 3 gigapixels, it'll take a picture every 15 seconds, and it'll take 2 of them to double check that they look right and that a cosmic ray hasn't gone through the chip and produced a duff pixel, for instance. So they'll take them in pairs to double check them. So every 30 seconds it will take 2 images and generate 2 lots of 3 gigapixels. So that's about 15 gigabytes of data. Once the telescope has taken those 2 pictures, whilst it's heading off to take its next picture, it will send that information down from the mountain top to the base of the mountain where the LSST HQ is. It'll do that over a 100 gigabit per second intranet link, and it will take about 1 second to send the 15 gigabytes down the mountain. At the La Serena headquarters, it will hold a local copy, just as a backup as it were, and then it will send the data via an internet link to North America. From South America to North America, it will send those 15 gigabytes in about 4 seconds over a couple of optical fiber links. You may ask, how do you possibly send 15 gigabytes over 4 seconds via the internet? Well, anybody can do that. Your optical fiber, if you've got optical fiber to your house, then that optical fiber can quite happily send data at very, very, very fast data rates. The reason you don't get anything like that, apart from the fact that you're not paying for it for your local internet service provider, the main reason you can't get these sorts of data rates is because the internet is chock full of YouTube videos flying backwards and forwards. Most of these videos, I'm told, include cats. Now, if you could somehow stop the cat videos from going down your internet link, then if you put a block, if you put basically a cat filter on your internet connection, you can get information across the world in a matter of seconds. You can get gigabytes sent from A to B in seconds. So the idea is the telescope takes the images, and within about 5 or 6 seconds, they should be at the National Center for Supercomputer Applications, NCSA, in Urbana-Champaign, Illinois. Why do they get sent to Illinois? Because Illinois has a supercomputer center which will crunch the data and very quickly decide what is interesting in these images. It'll compare the two and tell if they're okay, and it will compare them with previous data, the previous night, the previous week, whatever. And it will come up with a list of things that have changed. It'll come up with a list of any object that's moved, whether it be an asteroid or a trans-Neptunian object. It will come up with a list of objects that have changed their brightness, whether that's variable stars or a supernova has gone off in a galaxy. It'll give you a list of objects that appear to have changed their colour, because they now look different brightnesses in different filters. And it's estimated that in a given night there might be 10 million events. In other words, 10 million objects will have changed their position or changed their colour or changed their brightness. If you wish, you can sign up for a text message if you're interested in any of these events. I don't suggest you sign up for all of them, otherwise you'll receive 10 million text messages every night. As well as producing this list of objects, which is going to be of great interest to the scientists, because, for instance, one scientist might be interested in new asteroids, and so they will sign up to be alerted to any objects that moves unexpectedly. Other scientists will sign up to tell me when a supernova has gone off. But in addition to all of these events that this supercomputer is generating, it will also catalogue the positions of every object that it sees in every image that it gets every 30 seconds. To start with, it'll start cataloguing. As time goes by and it co-adds a lot of this information together, it will be able to see fainter and fainter objects. After 3 nights, it will know about objects that are out there, but only down to a limiting magnitude of about 25 or so. As time goes by, it will have a limiting magnitude which gets fainter and fainter and fainter, and hence the catalogue will start to grow. Ultimately, the catalogue ought to end up as something of order 35 billion objects, some 20 billion galaxies, and 15, 16, 17 billion stars, that sort of level. So the catalogue is going to be huge. The amount of effort of the supercomputer just to crunch on this is going to be huge. And then the question is, what are you going to do with the images? Are you going to use artificial intelligence to actually go through all of this? Are you going to use crowdsourced people to look at these things to try and pick out interesting objects? But think about it. A single image is 3 billion pixels. If you give that image to one person, they haven't even got time to scan, even cursorily, the entire image to see, oh, something interesting looks like it's going on down in this bottom right-hand corner. So I think it's going to have to be a large element of artificial intelligence applied to look for interesting things to follow up with other Earth-based or space-based telescopes. There will be an app so that everybody can monitor what's going on. What did the LSST find last night? How many supernova went off last night? How many asteroids are moving towards Earth? Are we going to die the day after tomorrow? There will be an app that allows you to follow these things, and there's going to be an alert service that allows you to be told if a variable star suddenly gets a lot brighter or a lot dimmer, or suddenly starts behaving very oddly. So the LSST has been on the horizon for a little while now, but now it's really close. I don't know quite what the current date is for the operation. 2022, I'm guessing, has been put back to 2023, but it's not that far away. A final point about the labelling of these things. The LSST is the Large Synoptic Survey Telescope. But just to confuse everybody, a little while ago they decided to rename the LSST Observatory the Vera C. Rubin Observatory in recognition of the contributions that Vera Rubin made in measuring dark matter in the 1960s, looking at rotation curves of stars going around galaxies. So the LSST Observatory is now the Vera C. Rubin Observatory. The telescope itself has been renamed the Chamonix Survey Telescope to acknowledge the fact that private donors have put cash on the table, and so the telescope has now been renamed. But they wanted to keep LSST, and so they've decided that the survey that it's going to be doing is now called the Legacy Survey of Space and Time. So although LSST used to be the acronym for the telescope, LSST is now the acronym for the survey that the telescope is going to carry out. That means that lsst.org, the domain name of where you find the web page of all the information, they didn't have to throw that away. They could keep the domain name because they've kept the acronym LSST, even though it now means the survey, not the telescope. There you go. So LSST, if you don't spell out what it means, it can mean pretty much anything you like. So I've told you why we need another survey, despite having had a few in the last century. I've told you why it is that we need a better telescope than simply reusing an existing telescope. I touched on some of the science that the LSST is going to deliver, but mostly it's going to provide information for other telescopes. I've given you an indication of how the technology will deliver that in terms of the novel optics and the novel camera. And I finished with just an idea of how the survey is going to work and how some of the data is going to be handled. Interesting times ahead. Thank you all for listening.